Welcome, blockchain developers and enthusiasts, to today's session of Solidity to Rust. I'm Julian Martinez, Senior Developer Advocate at SDF, and your host for today's session. We're here to explore the comparison between Solidity and Soroban data types, which will help facilitate a smooth transition over from the EVM to Soroban. And remember, for an in-depth understanding of migrating from the EVM, you can always reference the documentation. I personally created a 4-part series that you can check out and reference throughout your developer journey. The link is provided in the description below, and I encourage you to take a look if you have a chance. So, what are data types? Data types play a fundamental role in programming, defining the kind of data being handled. They not only guarantee data integrity and consistency, but also enable efficient memory allocation, thus optimizing resource usage. These types can be broadly categorized as primitives, such as booleans and integers, and non-primitives, such as structs, mappings, and enums. Proper utilization of data types is crucial for robust and efficient programming, especially in smart contract applications. So let's go ahead and kick this off with a side-by-side code comparison. In our Solidity contract, we work with several data types, including primitive types like Boolean, integer, address, and strings. And additionally, we have non-primitive data types such as structs, enums, and mappings. And on the Soroban side, at the top, we're importing the data types that we'll be referencing throughout the smart contract, and we see some of the same data types as before, such as Boolean, unsigned integers, enums, and structs. We'll dig into this more as the session evolves, but let's start off with the basics. In both Solidity and Soroban, you can declare data types as constants or mutable. For example, Boolean types can hold true or false, while uint types can store arbitrary numbers. Something I like to point out is that in this example, we're leveraging the data type string on the Solidity side, but on Soroban, we leverage the data type symbol. Here, we're using a short symbol. Short symbols are strings with 9 characters or less and provide improved runtime efficiency. While symbols up to 32 characters are allowed, using shorter symbols offers better performance and allows for compile time computation. We use the symbol data type in the same way we use a string type in Solidity. Here's an example. So here, in our short symbol example, you can see the string example. To get a longer string, we'd have to pass an env through a function. Moving on to our next data type, addresses. In both Solidity and Soroban, addresses are leveraged to record and store addresses on EVM and FutureNet respectively. Addresses can represent various account types in Soroban, including classic Stellar accounts, custom accounts implemented on Soroban, or arbitrary contracts. Here's an example of how they look on FutureNet. Both Solidity and Soroban use the address data type to store and retrieve addresses on EVM and FutureNet respectively. Addresses can represent various account types in Soroban, including classic Stellar accounts, custom accounts implemented on Soroban, and arbitrary contracts. Here's an example of what a contract address looks like on FutureNet. And here's an example of what a wallet address looks like on FutureNet. As you can see here, the wallet address begins with G and the contract address begins with C. Soroban addresses can leverage authorization functionality, enabling the implementation of custom authentication rules directly into the smart contract's logic. Here's an example. I'll call the method setAddress, which stores an address to the smart contract. In this case, we'll set a preset address, Alex, to the smart contract. Now, I'll call a similar function, but this time we'll leverage the require auth function. This means that the address, in this case, parameter A, must meet the required authorization for this call to succeed. As you can see here, the call failed because Alex's address was not authorized. Now, I could authorize this address and this call will succeed, but I just wanted to showcase the advantage of Soroban Rust as it eliminates the need to import external contracts to enhance security. With the Soroban Rust SDK, we can directly utilize authorization on addresses and leverage its built-in functionality for secure smart contract development. If you want to learn more about authorization, take a look at our Soroban docs for technical documentation or our Soroban examples for real-life implementations. We'll link both in the description below. In Solidity, strings handle variable-sized text data, while bytes handle variable size byte data. Here's an example of how it looks on Solidity. So we'll expose our string here, message, which is hello world. We'll then transform that string into a dynamic bytes value, and then we'll transform that dynamic bytes value into a fixed bytes value. So as you can see here, we transformed this dynamic bytes value into a fixed bytes value of 32 bytes. Here's how this looks on Soroban. Similarly, we have the string hello world. We'll transform that into its bytes value, and then we'll transform that into its fixed bytes value. It's important to specify how Soroban differentiates between fixed bytes value data types and dynamic byte value data types. Here, we use the data type bytes to specify dynamic bytes and bytes n to specify fixed bytes. As you can see here, in the method getBytesN, we get return data of a fixed bytes variable specified to have 32 bytes. Next, we'll cover arrays and the vec type. In Rust, the equivalent of Solidity's arrays is the vec type, which offers the flexibility of resizable arrays. Here's an example of how the data looks on Soroban. So we have our integer arrays, we have our symbol arrays, and we have an example of our address arrays. And the same thing over on Solidity, we have an address array, a unit array, and a string array. Next, we'll cover structs. Structs are user-defined data types in Solidity, but are also available in Rust. They serve the same purpose of encapsulating related data. Here's an example of how this looks on Solidity. As you can see here, we have this example struct that passes the data type string and uint. We've predefined this example struct to have the string struct and the uint 999. Here's how the data look when it's called, and here's how it looks on Soroban. Here's how the data looks when it's retrieved, and we'll go over to structs on Soroban. Now, there's two different types of structs on Soroban. Namely, we have the named field struct, where you have to specify a name for each field, as well as the data type, and unnamed field structs, where all you have to do is specify the data type that you want to retrieve. Here's an example of how the data looks when it's called. So to reference the data that's in the field name, all we have to do is reference the name field. Similarly, all we have to do to reference the field amount is reference the amount name. So I'll go ahead and get that data. We have struct and we have 999. On our unnamed field, we have to reference the slot where the data lives. So here we have slot 0 and slot 1. So we have struct 2 and 777. Structs are great because you can store different data types in one object, making for a dynamic coding experience. Next, let's move on to enums. Enums are valuable for managing states and simplifying conditional logic. Enums enable the definition of custom data types with a finite set of values. Let's go ahead and check out how enums look on Soroban. I'll go ahead and initialize this enum, example enum, with an address, another address, a uint, and a symbol. Let's go ahead and retrieve that data. As you can see here, both addresses, the uint, and the symbol were returned. It's important to note that on use Soroban, they use predetermined addresses, but here's how an address would look on a FutureNet setting. One cool thing about enums on Soroban is that they come in two different types. Here, we're working with a unit and tuple type enum, where we can actually store different data to different slots within these, where we can actually store different data to different slots within the enum. For example, if we reference C, we're going to go ahead and pass a U32 as a key and then go ahead and retrieve a value. Here's an example. So we'll go ahead and reference slot 1 and we'll set the value of. Now, when I get the slot 1, I get the value 100. This is great because you can create a kind of key value system. If I wanted to, I could specify this slot to be an address. And similarly, I could specify this slot to be a symbol. Moving on, we have integer enums. In both Soroban and Solidity, integer enums are commonly used to represent different states for options within contracts. Here's how it looks on Solidity. We're looking at the enum, status enum, which represents open, closed, and pending. Let's go ahead and get this data. So we have open, closed, and pending. Similarly, on Soroban, we also have open, closed, and pending, which are defined as 0, 1, and 2. So we'll get the status for open, we'll get the status for closed, and we'll get the status for pending. Now, this is a simple demonstration of how to use integer enums, but for a more complex contract utilizing enums, such as in a crowdfund scenario, you can explore the Soroban example dApp to see how enums are leveraged to set the state of a crowdfund campaign. Next, we're going to move on to mapping and maps. In Solidity, mapping is used to create key value pairs, and in Rust, we use the map type for similar functionality. Here's an example of mapping in Solidity. Here we have our map address uint map, where we're mapping an address to a uint. So I'll go ahead and set the key as a random address. And I'll go ahead and set the value as 100. Now, when we reference this address in our map, we get the return value of 100. Here's an example of how it looks on Soroban. In this get map method, we're creating a map that takes in the key of an address and the value of a uint. Let's go ahead and see how this looks. We're going to define the address as Alex, the value of 100, key 2 as Bart, and the value as 200. As you can see here, the data was returned where we have our keys and values. Similarly, we can leverage Soroban storage, where we could set a key and a value to the smart contract. Here, we'll set a value to an address, Alex, and we'll set the value of 100. Then we'll go ahead and retrieve that value from the smart contract. So now when we reference the address of Alex, we get 100 returned. And there you have it, a comprehensive guide to transitioning from Ethereum's EVM data types to those on Soroban. And remember, the Soroban documentation is an invaluable resource for detailed understanding of things like migrating from the EVM and an introduction to the Rust smart contract dialect. Feel free to join our Discord community if you have any questions or need further clarification. You can reach me at the godhand #0021, and don't forget to explore the Soroban example contracts, which offer real-life implementations to help you fully leverage Soroban's capabilities. Until next time, happy coding.